Good morning, everybody. Okay, in this section of Calculus 3, we're going to talk about Chapter 14, Section 5, Directional Derivatives and Gradient Vectors. Basically, all we're doing here is now we're involving vectors in our derivatives. When you involve vectors, you involve giving the derivative a direction. So derivatives involving vectors that give them direction. First section, directional derivatives in the plane. So let's talk about this now. So let's say f of x, we have a function f of x that is differentiable and therefore has a rate of change. The rate of change of our function with respect to t so we're defining our function. It's a function with respect to t. So even though it says f of x, f of xy, xy are subfunctions with respect to t. The rate of change along a differentiable curve is defined this way. Well, it has to be differentiable because it involves rate of change. We parameterize like this. X is equal to some function g of t, and y is some function h of t. Remember, they're with respect to the function value t. So at any point along this curve, p sub 0, which is x sub 0, y sub 0. So any point, since x of 0, x and y are subfunctions of g and h, we're saying that point is a function of t at 0 and h at 0. So the rate of change with respect to t along the differential curve is parameterized by these two functions. At any point p sub 0, which is actually p g of t sub 0 and h t of 0, the rate of change with respect to t increasing with increasing t. F of x is differentiable and therefore has a rate of change. The rate of change of f t with respect to t along a differentiable curve is parameterized by x and y. At any point on the curve, p sub 0, the rate of change with respect to its increasing t. T depends on the direction of motion along that curve. So even though it's moving, the rate of change, even though it's moving, it's changing, it's the direction that's important to us. So it's, if the curve is a straight line and t in the domain is the arc length perimeter, the line measured from our p sub 0 in the direction of a given unit vector u. So if the curve is a straight line and t is the arc length perimeter along the line measured from p in the direction of the given curve, then the derivative of the function with respect to t is the rate of change of f with respect to the distance in the direction of u. So the derivative is the rate of change of f, the distance to the direction of the vector u. So as u changes, the rate at which f changes with respect to the distance as the point as u changes, the rate at which the function f changes with respect to distance as the point moves through p sub 0 in different directions. Okay, it's a vector, and if it use a vector, as long as you have a vector, each point along the way the values change, and that changes the direction. Let f of x, y, here are the conditions for it. It has to be defined throughout region R. Since we have a region, we have an xy plane. P sub 0, x sub 0, y sub 0 is a point in the region R and lastly, the vector u is defined as u1i plus u2j. Be a unit vector. So that affects all this. And the equations x equals x sub 0 plus s, the u component of our unit vector, and y is equal to the initial point, y value, plus s u2. And those equations are the parameters, parameterize the line through p sub 0 parallel to u. This is the important part. So once we parameterize it, we have our unit vector. We have a point that function is going through in the region. Then these values of the parametric equations are the line through p sub 0 and parallel to the unit vector. If the parameter s measures the arc length from the point p sub 0 in the direction of u, we find the rate of change of the function at p sub 0 in the direction of u by calculating the derivative with respect to s. Cal Q 18. The derivative of f with respect to s at that point, p sub 0. So here's notice. If the parameter s measures the arc length from p sub 0 in the direction of u, we find the rate of change of the function at p in the direction of u by calculating the derivative of f with respect to s. Here's the formal definition. The derivative of f at p sub 0, which is x sub 0, at some point x sub 0, y sub 0, in the direction of the unit vector u, which is made up of u sub 1i, u sub 2j. The derivative is the number df over ds at po onto u, not onto u, but in the direction of u. It equals the limit as y equals 0 x sub 0 plus s u sub 1, comma, u sub 0 plus s u sub 2 minus the initial point x sub 0 y sub 0 all over s, because we're taking it with the derivative of s, providing it exists, of course. So the derivative of fx at that point of 0 in the direction of the unit vector u is the number given by the limit of x sub 0 plus s u sub 1, y sub 0, s u sub 2 minus the original function. The directional derivative defined above is also denoted by the functions, the d for directional derivative of f of at p sub 0. That means it's just x sub 0 and y sub 0. This says the derivative of f in the direction of u at p sub 0. The derivative of f, that's that one, in the direction of u, that's with capital D is the directional derivative of f, in the direction of u at p sub 0. And that's how you read that. Okay, let's look at the partial derivatives. The partial derivatives, f of x at x sub 0, y sub 0, and f of y at x sub 0, y sub 0, are the directional derivatives of f at p sub 0 in the I and j directions. All right, so this is our first example. Example 1. Find the derivative of f of x equals x squared plus xy at point 1, 2 in the direction of the unit vector u equals 1 over radical 2I plus 1 over radical 2j. Fix my earphones here. All right. So my limit function, we're going to be using the limit function because we're looking for df ds, which is the limit function as s approaches 0 x sub 0 plus s u sub 1 y sub 0 plus s u sub 2 minus the initial function. So this is u sub 1, this is u sub 2. And that's our function. So I need more room here. So we take the first, this function, and put u1, u2 in there. So x is defined as this, which is x sub 0 s u sub 1 squared x sub 0 plus s u sub 1 y sub 0 plus s u sub 2 minus our function x squared plus xy. this, I'm sorry, so the limit as h approaches 0. Now, this is our x sub 0, y sub 0, and that's u1, 2. So let's plug those in there. The limit as s approaches 0, x sub 0 is 1 plus s. U sub 1 is 1 over radical 2. That's the first one squared. X sub, so repeat this one. It's 1 plus s over radical 2 squared, not squared, times 2 plus s over radical 2. Because that's what u1, u2 are. Minus so now plug in our x and y values. 1 squared plus 1 times 2 over s. The limit as s approaches 0, so we foil this, so we end up with 1 plus 2 s radical 2 plus s squared over 2. We did 1 plus s over radical 2, 1 plus s radical 2. 1 times 1, s radical 2 is 2s radical 2. S times s squared, radical 2 is that. And then now these two. 1 times 2 is 2, plus s radical 2 plus s radical 2 makes it 3 s over radical 2 plus s squared over 2. One squared is 1, plus 2 is 3. The limit as s approaches 0. So 1 plus 2 is 3. That cancels with that. We have 2 plus 3, 5s radical 2 plus 2s squared over 2 over s. S squared over 2 plus s squared over 2 is 2s squared over 2. Those cancel. Limit as s approaches 0. 5s over radical 2, s times radical 2 plus s squared over s. The s's cancel here. So we have the limit as s approaches 0 of 5 over radical 2 plus s. S goes to 0. we end up with 5 radical 2. Next page. Yeah, that's what, since we're finding the derivative, we're looking for the rate of change. So the rate of change of this function at this point through in the direction of u is 5 over radical 2. Right? Let's look at interpretation of the directional derivative. Let z equal the function f of x, y. That represents the surface S in space. If the initial z sub 0, which is at f x sub 0, y sub 0, lies on S, this is a small case, because now we're using S as surface space. It's actually the length. So if z sub 0, f of 0 lies on F, actually the point P sub 0, which is x sub 0, y sub 0, z sub 0, lies on F, because all the points that make up the curve. Then the vertical plane passing through P and P sub 0, which is x sub 0, y sub 0, and is parallel to the unit vector u. It intersects S in a curve C. So you have the function z. If at some initial point z sub 0, the point lies on S, then the vertical plane passing through the point P and P sub 0 is parallel to the unit vector u, and it intersects the surface in a curve C. So it's a plane cutting through a curve in space. the rate of change of SF in the direction of U. Remember, in calculus 1, the rate of change is the first derivative. So the rate of change is the slope of the tangent line or plane to the curve C at point P. This is, of course, when we first started this subject, this is in the right handed system that is formed by the vectors U and K. Just two separate vectors. So when the vector U just equals I, the directional derivative at P sub 0 is the partial of F with the partial of X at some point X sub 0, Y sub 0. That's if we just have the I component, which is the X component. When the vector U just equals J, the directional derivative at P sub 0 is the partial of F with respect or over partial of Y at the point X sub 0, Y sub 0. The directional derivative is a generalization of the two partial derivatives, generalizes the two partial derivatives. Okay, notice how we're looking at the unit vector U with respect to I and J. Until now, the rate of change of any function f of x, y, or it could be 3 dimensions, was only in the I and J directions. Now we can find it in any direction of the unit vector. So remember, so now it's important that we have to find our unit vector when we're trying to deal with directional vectors, because that's going to be, as we've seen in our formulas earlier, x is x sub 0 plus s u sub 1, and y is y sub 0 plus s at u sub 2. Let's look at the calculations and the gradient. That's it, the gradients. To calculate the directional derivative of f, step 1. Begin with the line x equals x sub 0 plus s u sub 1 by parametrizing, and y equals y sub 0 plus s u sub 2. Begin with the line going through some point p sub 0, x sub 0, y sub 0. The line is parametrized with the arc length parameter s. It's increasing in the direction of the unit vector u. Where u is equal to u1i plus u2j. Then, using the chain rule, we get this. Remember, we start with the derivative of f with respect to s, the arc length parameter, at u and po. What we get here is the partial of f with respect to x, p sub 0. Then we get the derivative of x with respect to s. That's the first part, and we do the same thing with the other. The partial of f with respect to y at p sub 0, and the derivative of y with respect to s. What this represents then is the partial of f with respect partial of x at p sub 0 u sub 1 plus the partial of f with respect to y at p sub 0 at u sub 2. So u1 is defined as a derivative of x over s, and u2 is a derivative of y over s. What that equals, because now we have to put it in terms of I and j. The partial of f with respect to the x, I, plus the partial of f with respect to y, PO j, dot u1i plus u2j. This gives us the derivative of a differentiable function f in the direction of u at point p sub 0. This gives us the derivative as a dot product of u with a special vector. Remember, whenever we get dot products, we always get scalars. And all it is the product of the I components plus the product of the j components plus the product of the k components, add them together, and it'll give you the dot product. Okay, the special vector is called the gradient vector. The gradient vector, or so just call it the gradient. We have symbols for it. I'll get to that in a second. Of our function is the vector del f equals the partial of f with respect to the partial of x, I, the partial of f, the partial of y, j. And if we had third dimension, we'd put the k one there. The value of the gradient vector obtained by evaluating the partial derivative with partial fx, partial fy at a point p sub 0, x sub 0, y sub 0. The value of the gradient obtained by here's so whenever you write the gradient vector, that's what this symbol represents. That's, well, that's the next page. This del function of f, del function of f with respect to p at po, or del function of x at the point xo, yo. And all it is the partials of x and y. This notation is read the gradient of f, or grad f, or the most common one that people use is del f, because this symbol here is referred to as the del. Actually, it's got a couple other names. It's also called aka the nabla, or atlid. This is an interesting one because remember earlier we talked about this function, which is a delta function, but this one is upside down, so they spelled delta backwards. But whenever we see this function, we call it the del function. It was invented in the 1800s by a guy named William Hamilton. It's known as the Hamilton notation, or Hamiltonian operator. It's used in vector calculus. Here's a theorem for it. The derivative is a dot product. If f of xy is differentiable in an open region that contains p sub 0 then the partial of f, which is partial with respect to partial of s, p sub 0 is equal to the dot product of del f at p sub 0 dot the unit vector u. The dot product of the gradient del f at p sub 0 with the vector u, it can also be written as so it just makes it much easier to look at that. All right, so what we're saying here is that now a derivative is it actually a dot product with the gradient vector, or the gradient of f times the unit vector. All right, let's look at the second example. Find the derivative of f of xy equals x e to the power y plus cosine xy at point 2, 0 in the direction of v. All right, recall from our notes that our formula that we have to deal with, since the derivative in the direction, we need to find those. Del f is simply partials of x and y, and use a vector v over magnitude of v. So the first thing you have to do is to find the magnitude of v, which is 3 squared (9 plus 16), which is 25, which is 5. So our vector u is 3 over 5i minus 4 over 5j. Now we have to find, so the first thing, we have to find u. So we have to find this and that. So we took this divided by that, that divided by that. So the next thing we do is find the partials of x and the partials of y. So f of x with respect to x, derivative of x will just leave us e to the power y. Derivative of the inside, x times y, derivative is y, times negative cosine, negative sign. So that changes. And then we do the same thing with the y. Partial of y, derivative of e to the y is e to the y, so it's x e to the y. Same thing there, but instead of y, we have x. We have negative x sine xy. Our point is at 2, 0. So we have to take it at our point 2, 0. So anywhere you see an x, put a 2, and a y is 0. e to the 0 is 1. 0 times anything is 0. So the partial with respect to x is 1. The partial with respect to y is 2 times 1 minus 2. 2 times 0 is 0. The sine of 0 is 0. So we just have 2. All right, so since we had the partials of fx, fy, we know our del function, our gradient at 2, 0 is equal to 1i plus 2j. Let's recap that. Del f at the point 2, 0 is actually the partial with respect to x at 2, 0 I plus the partial with respect to y at 2, 0 j. So that's my gradient. The derivative of f at our initial point 2.0 in the direction of v is remember we have to take it with respect to u. Even though it says the question says we want it with a v, in order to find the actual value, you have to find the unit vector u. So that equals del f at 2, 0 dot with u. Del f is I plus 2j dot our u function was up here, which is 3 over 5i minus 4 over 5j. To find the dot product, 1 times 3 over 5 plus 2 times negative 4 over 5 is 3 over 5 minus 2 times 4 is 8 over 5 equals negative 5 over 5, which is negative 1. Just negative 1. So that's the derivative of the function f of x at 0.20 in the direction of v. All right. We can also evaluate the dot product using the trig functions. That's horrible. that equals the magnitude of the del function, the magnitude of u cosine theta, which is just well, theta is the angle between the vectors u and del f. The properties of directional derivatives the function f of x increases most rapidly when the angle cosine of the angle between the two vectors equals to 1. Along the horizontal. And u is the direction of the vector del f. So in other words, looking at this equation here, so it increases most rapidly when because we have that as our definition. When cos this equals 1, when theta equals 0, so it increases most rapidly at the magnitude of f. F of x, y decreases most rapidly in the direction of negative del f. Or when cosine theta equals -1, which is at pi. So it increases most fast there and decreases the fastest here. And lastly, any direction defined by u orthogonal to a gradient del f not equal to 0. is the direction of zero change in F. Because theta equals pi over 2 and cosine theta or cosine of pi over 2 equals 0, which tells us then the magnitude of F times cosine pi over 2 is 0. All right, let's take an example here. Find the direction in which f of x, y equals x squared over 2 plus y squared over 2. Increases most rapidly at the point 1, 1, decreases at 1, 1, and what are the directions of zero change? Increases most rapidly. And the direction of del f at 1, 1. So the gradient there is so we find the partial of f, partial of x, partial of f, partial of y. Of course, with that 1, 1. So the partial of x is x squared over 2, which is just xi. The partial of y, derivative of y is 2y over 2. The y's cancel. And we're taking this at 1, 1. So x is 1, y is 1. So now its direction the del f over magnitude of, which is I plus j. The magnitude is 1 plus 1 square root of 2. So at 1 radical 2i plus 1 over radical 2j. That's when it's most rapidly. Increasing. Decreasing most rapidly at negative del f at 1, 1. So all that's really telling us is here it's u, so now we have to go negative u, which is negative 1 over radical 2I minus 1 over radical 2j. It's just the inverse. Now, what are the directions of zero change at 1, 1? Okay, here, let's use n instead of u. They cancel each other out, so they're opposites. And at negative n, which is 1 over radical 2I minus 1 over radical 2j. And that's all there is to those. Right. Let's see. Let's gradients and tangents to level curves. If f of xy is differentiable, and has a constant value c along a smooth curve, then we define r g of ti plus h of tj where's the where r is the curve part of the level curve. Of our function. Remember, well, you would define x as g of x, y as g of y, h of g of t, h of t. So if f is differentiable and has a constant value c, this is what we define as a level curve, and has a small smooth curve. If it's a smooth curve, if it's differentiable, all this stuff comes from the previous lessons. Then f g of t comma h of t is equal to some constant. Then differentiating both sides with respect to t gives us the derivative with respect to t of f g of t h of t equals the derivative of our constant with respect to t. What that means, using the chain rule of this, we get the partial of f with respect to partial of x times the derivative of x with respect to the derivative of t plus the partial of f with respect to y and the derivative of y with respect to t. The derivative of any constant is 0. Okay, if we have g and h in our functions, we have combine our terms. So we have, remember, we're dealing with vectors here. So we have a partial of f, partial of xi, plus partial of x, f, partial of yj, dot dg dti plus dh dtj. So this says that the del function f is normal or orthogonal to the tangent vector dr dt. This tells us that del f is normal to the tangent vector dr dt. So it is normal to the curve. Remember, we defined the smooth curve as dr, as r. So we take the derivative of r with respect to t, and if the del function is normal to the tangent vector r, then it's also normal to the curve. All right, let's look at paper. Tangent lines to level curves. All right, level curves are where the function has derivative set equal to a constant. So we have tangent lines to the curve. This gives us an ability to find equations to lines tangent to level curves. These lines are normal to the gradients. The line through a point zero, x sub 0, y sub 0. It can be any point because if it's differentiable, it's smooth. It means derivatives exist everywhere. So if line through a point has to be continuous, has to be connected. that is normal to a non-zero vector we'll define it as which is not it's a non-zero vector. It's normal to a non-zero vector. Has the equation a x minus x sub 0 plus b y minus y sub 0 equals 0. We'll build up on this. If I was going to say, yeah, if del f at our points x sub 0, y sub 0 is equal to the partial of f with respect to x at x0, y0, I, and the partial of y at x sub 0, y sub 0, j, and is non-zero then we get the tangent line to a level curve. So if the del function at the point is equal to the partials of both of those and is non-zero, then we get a tangent line to a level curve. This is what it looks like. F of x, x sub 0, y sub 0 at x minus x sub 0 plus f of x at x sub 0, y sub 0 times y minus y sub 0 equals 0. Okay, remember earlier we saw this as a x minus x sub 0 plus b y minus y sub 0. So that's what we're defining a and b as. Let's look at an example here. Find the equation of the tangent to the ellipse x squared over 4 plus y squared equals 2 at the point -2, 0. So first, find the gradient, which means partial of f with respect to x. So this becomes 2x over 4, which is x over 2. And the partial with respect to y is 2y. Right, so our del f at the point -2, 1 is equal to f of xi plus f of yj at -2, 1, which gives us x over 2i plus 2yj at -2, 1. So anywhere we see an x, put a -2. And anywhere we see a y, put a 1. Which equals to -I plus 2j. Now, because the gradient vector is non-zero, it equals something. The tangent to the ellipse at -2, 1 the tangent line, I should say tangent line. So we have, remember we said f of x, x sub 0, y sub 0 at x minus x sub 0, y, f of y at y sub 0. So this is our -1. X sub 0 is -2. Our y function was 2. Remember, here's -1, 2. Y minus y sub 0 is 1. Distribute these. We have -x. This becomes a plus. Makes it a -2. Plus 2y minus 2. Move the non-variables to the other side. We have -x plus 2y equals 4. Don't want to have a negative in front of here. So just change everybody's signs. There. That's the equation of the line tangent to the ellipse. That we just did example 4. So if we know the gradients of functions, we can calculate their sums, differences, constant multiples, product, and quotient. Those are in the algebra. following rules for derivatives of single valued let's see, instead of single variable functions. Here are the rules. In other words, the sum rule. You can add these if you have the del of two vectors, you can split them up. Likewise, you can have the difference. F minus G equals del F minus del G. Constant multiple. So you have some constant multiple to the function. You can bring that function out in front, the constant outside. All of these are the same as stuff that we've done with other functions. The product rule. F times G is the product. Here's where it gets different. We use the product rule here. So F times G, take the derivative of G. It's the same as we had derivatives of two functions. We do the same thing with dels. So take the G and find the del function of that, of F. Same thing with the quotient. So G del F minus F del G over G squared. Okay, these G and F are scalar multiples. For these two. So those are the rules that we're to live by. Right, let's look at example 5. Let me get some paper. I'm out of paper. All right. For the following information, f(xy) is x minus y, g of xy is 3x. So del f is I minus j, the del g is 3j. Prove the difference and then prove the product. So we have f minus g, which is equal to So we have x minus y, that's f, minus 3y. One y minus 3y is 4y. So this becomes I, parameterize them. We get I minus 4j. Which is, since that's true, then that's the same thing as saying I minus j minus 3j, which is del f minus del g. The product. We multiply f times g. So we have x minus y times 3y. Three xy minus 3y squared. They both have a 3y. I can take that out. That leaves me with x minus y. So that's just y, it's j. I minus j, which is equal to the same thing as the product of those two. The proof is not really that necessary. It's just self-explanatory. It's just straightforward. Just add the coefficients or subtract the coefficients. Functions of 3 variables. F of x, y, z be a differentiable function. And u equals u1i, u2j, a unit vector. Oop, I forgot k. Be a unit vector in space. We then have del f is the partial of f partial of xi, partial of f partial of ij, partial of f partial of zk. And du of f is equal to the del of f dot u, which is equal to partial of f partial of x times u1 plus partial of x partial of y u2 plus partial of f partial of z u3. So the directional derivative can be written as f dot u, which is the magnitude of del f, the magnitude of u, cosine theta, or just magnitude of del f cosine theta. As before, the function f increases most rapidly in the direction of del f, decreases most rapidly in the direction of negative del f, and in any orthogonal direction to del f, the derivative equals 0. Again, it's the same thing, but now we have three dimensions, or three variables. So get the next example. Example 6. Find the derivative of f of xyz, x cubed, xy squared minus y at 0.110 in the direction of v. Then b. In what direction does f change rapidly at p sub 0? And what are the rates of change in these directions? All right, so A. We have v. We have to find u. So we have v. We need the magnitude of v. Four plus 9 plus 36. 49 is 7. So u equals 2 over 7i. 3 over 7j, 6 over 7k. That's the first way to find it now. Find del f at our point, which is 110. So our function is x cubed xy squared minus c. So f of x equals 3x squared minus y squared. F of y is minus 2xy, and f of z is -1. At 110, so x is 1, y is 1, z is 0. So 3 times 1 squared minus 1 squared is 2. -2, 1, 1 is -2. And at 0, it's -1. So our del function at 1, 1, 0 equals 2i minus 2j minus k. So now we got to find the derivative of f at p0 in the direction of v. And that's the del f at 1, 1, 0 dot u, which is equal to 2i minus 2j minus k dot 2 over 7i, 3 over 7j, 6 over 7k. So 2 times 2 over 7 is 4 over 7i. Well, no, we're doing dot product, so there's no ij anymore. So we have 2 times 2 over 7 plus -2 times -3 over 7 plus -1 times 6 over 7. That equals 4 over 7 plus 6 over 7, 2 times 3, minus, these two cancel, so the answer is 4 over 7. These two cancel, so it's 4 over 7. So that's A. Now, in what direction does F change most rapidly at P sub 0, and what are the rates of change in those directions? Six B. Okay. Increases most rapidly in the direction of del F, which is 2ij minus k. Decreases most rapidly in the direction of negative del F, which is negative 2i plus 2j plus k. And the rates of changes in the direction right, 2 squared plus it's the magnitude of del F, or plus 4 plus 1. So that's for the first one. That's for the increasing. Now the decreasing. We have the negative of del F, which is the negative of 3. All right, that's section 5. I'll get the homework assignments out pronto. Good luck, everybody.